It's my pleasure to introduce Edoardo Airoldi. I have known Edo since he was a PhD student in Carnegie Mellon. We met back in 2008 when we were all into mixed membership models. Really loved the mixed membership models back then. And I'm sure that you guys have read or will read one of the seminal papers in this area, which is the mixed membership stochastic block models. That was published in JMLR, the Journal of Machine Learning Research, back in 2008, actually it came out. Again, we were all like mixed memberships, they're everything, right? So anyway, so Edo is an associate professor in the statistics department at Harvard. And so he's been there since 2009, and he leads he directs the Harvard Laboratory for Applied Statistical Methodology and Data Science. He got his PhD at Carnegie Mellon, as I was saying. He has a background in statistics as well, so computer science and statistics. And he did a postdoc with David Bly. David Bly did the inverse allocation at Princeton. And so he has papers in the Annals of Statistics, Journal of American Statistical Association, Nature, PNAS, obviously Journal of Machine Learning Research, etc. Many, many awards, including like the Alfred Sloan Research Fellowship, fellowship at the Radcliffe Institute of Advanced Studies, and his research is at the intersection of, I would like to call, statistics, network science, and machine learning. And he's done some really good work on, for example, experiments. I know that David and Chris do that in terms of models and theory, our Dima here, and algorithms being computer science. So thank you very much for coming and talking to us about this.
Thank you very much. So, as Tina was saying, I thought, not a lot of people know me here. So, what I think I do is exactly statistical elements of network science. And over, the past 15 years, I worked on several different problems. I started working on the statistics of networks when it was unpopular. And now, it's a very popular topic, so it's great. And obviously, we have institutes around the world that attest to that. And I worked on very different problems. So mixed membership was about modeling networks. Even prior to that, I worked on dynamic processes on a static network, like local area network, and how communication flows across computers. And there's some interesting statistical problems there. And several other problems I'd be happy to talk to people about. But today I'm going to focus on the last 5 years of my own research with my students. On networks, it's about how to design an experiment and how to design a controlled randomized experiment, you can think. And that has swallowed my entire, attention span and my entire lab and countless lives and things like that. So it's fun. So the motivating question is a question, we'll call it the Google question. It's a question that was posed to me during my sabbatical there in the New York City office. And so they run a lot of A/B tests, and I can be more precise about, in what product and in what space of Google A/B tests are run. But, let's just leave it at that. Think of A/B as auctions with two reserve prices, and the question is the extent to which raising the reserve price on an auction is going to raise total lift, in revenue. Okay? And they also have a lot of metrics they're interested in, but the simplest possible way to think about it is, a binary intervention and estimating total treatment effect in an advertising context. You could also think at a different use case where you have two different algorithms, and the goal is for ranking news, for instance, on your feed on LinkedIn, on your feed of Facebook. Now, if you put your classical statistical causal inference design of experiment hat, there's lots of issues with designing this test, and that's why the question was posed to me. So there's dependent outcomes, and one way the outcomes may be dependent through a network. There's strategic behavior that advertisers are obviously following. There's a very dynamic environment. There's heterogeneous units, there's both eBay advertising and local mom and pop shop advertising. And so how do we take these complications into account? Well, statistical classical theory says, well, just ignore them. They don't really matter, okay? But in a corporate setting and in a lot of social science settings, a lot of the causal effects we are interested in are actually effects due to these complications, and so assuming them away is untenable. So the immediate answer that they were themselves trying to propose at the time was, oh, we have lots of models of predictive user behavior or predictive advertiser behavior. We want to use a model to sort of deal with some of these complications. We can model some of these complications. And the statistical question is, okay, but how do we use a model to design a valid A/B test? Okay, and I'll have something more to say about what valid means, but it's important. Okay. Okay, and so these are a couple of approaches to designing an experiment when there's a model. Okay, so trusting the model, this is a high-level view. I'll be more precise later. Having a high-level model is typically not recommended because if the model is correct, it's great. You get no bias in estimating your causal effect, and you're very confident about it. If the model fails, well, you're in the worst possible situation you could be, because now you pay a price in unknown bias, you get a bad number, but you're still very confident about it. Okay, because model-based is essentially using model variation. Okay, and if you have a large number of data points, the model, that kind of variance is going to be very tight. So ignoring the model, which is what the Food and Drug Administration does, for instance, when running clinical trials, is conservative and safe. And I have something to say about the safe part. But so what this ignoring the model approach does, it leads to no bias. No matter what, you're going to have a good number at the end of the day. But you have relatively higher variance. Okay. And now I say sort of safe because, well, this is a good place to be. But the theory that we use to convince ourselves that this approach is safe, again, assumes away a lot of the complication that might be in your study. And so it is safe under ideal conditions, but not under more realistic conditions. Okay, so unless you are designing an experiment like the FDA under ideal conditions, then there's a problem. And the approach we are sort of proposing, and it ended up then eventually being used, is to use a model in a different way that people would naturally use. So we use a model-free estimator. So, and this is contrasted to the model-based approach where you have a likelihood, you're going to have a model-based estimator like maximum likelihood or method of moments. So if you have a model you believe in, you're going to use it to derive the estimator. But here's different. We're going to take an estimator which is very simple, but we are going to impose model-dependent constraints on the way we assign treatment. Okay? So that, I'll be very precise, but what that entails at the end of the day is that if the model is correct, you're in a great situation, you get no bias and low variance. And if the model fails, you get no bias, but you still get no bias, and of course you pay a price in terms of variance. That's a better situation to be in because it means you always get a good number, and you're gonna gain efficiency, lower variance, to the extent that the model is true. And so if you're in a company setting where you believe your models, well, this approach is viable. Okay, all right. And so now, before getting into more details, I want to, be very clear for everyone about what I mean by valid. So in the model-based approach, one way to fix ideas is to think about just regression models, where yi is the outcome, let's say total money spent in an auction, okay, or by advertiser I. This is alpha, the average sort of expenditure, beta times xi, let's say this is like a covariate, for instance, the budget. If you're a big firm and beta is positive, you're going to spend more money. And this is the effect of treatment, okay? Think of zi being a binary variable. I put you in an auction that has a higher reserve price, or I put you in an auction that has the standard reserve price. And tau is how much more money I can squeeze out of this advertiser if I put this advertiser in the auction with higher reserve price. And then there's epsilon, okay? And at the end of the day, the randomness in this system, in this type of analysis, only comes from the epsilon. That's why it's model-based. In contrast, what the FDA does, has a model like this where there's no epsilon, and so there is no model-based variation, so it's very safe in that sense. There's no model at all in this setting, and the variance comes from the way you assign treatment. Okay, so you can think of, if you have n people or n advertisers, there's a binary vectors of zeros and one, that each vector is one way of allocating treatment. But there's many such vectors. You put the distribution over the space of vectors, and that distribution is what generates randomness for this estimation problem. Okay, and so we're going to call this model-based, and there's a model and there's an epsilon. And design-based typically doesn't have an epsilon, and the randomness comes from z. And in our setting, we're going to have both an epsilon and a z, so the randomness will come from two different sources, but we're going to structure this variance or this variation in sort of an interesting way that I'll tell you about. Okay, so that's a very high level picture. So now, what I think I'm going to do is to give you a couple of concrete case studies on problems I worked on in the industry space and in the social sciences space, so that we all can think concretely about the problem. Then I'm going to have a couple of slides about what fails if you were to assign treatment in a completely randomized way, or with classical strategies that ignore the network. And then we're gonna get to the idea. Okay. So the first use case, the first application is these experimentation platforms and APIs within companies. Think of Google, think of LinkedIn. Each of these large companies has an experimentation platform. If you want to test whether your new algorithm or your new way of running an auction works or not, you're going to go to the group that owns the API for experimentation, and you're going to use the API to run an A/B test. Okay? And so this is essentially done in the industry world to A/B testing at scale products or auctions and things like that, or algorithm. And there's consequences of that. There's a vast archive of past randomization that you might do, that you might use for other purposes. Okay, and in this case, networks are present, but they're often an artifact, meaning they provide limited or partial view of interactions among the units. Units be users or advertisers. And interaction is important because it really, there is no notion of a social connection or anything like that. You have to decide what the network means in this context. And at Google, for instance, if the units are advertisers, the edge will mean that two advertisers are participating in the same auctions, okay? And so if you have a constrained budget and you're participating in multiple auctions and you're competing, well, then these auctions should, the revenues generated in these auctions should be related somehow. So now, in this world, there's a lot of challenges and opportunities. So the opportunity is that the state of the art in tech is very outdated, okay? So they all do completely randomized experiments, or they do at most cluster randomized experiments, okay? And there's some theory for it, again, for these two types of randomization under ideal conditions, but they will fail. And there's a lot of opportunities for intellectual scholarship, because a lot of the problems that they have don't really have a solution, any solution, okay, if you look in statistics, for instance, in the literature. Even, new textbook, like 2015 textbook, there is really no solution. It's an issue, okay? And from our perspective, working with company is great because they have an interest in making more money faster, okay? And for them, it's very cheap to experiment, because they will just say, okay, I can throw 1% or 2% of my 1 billion users in your experiment, and you can try and assign treatment to them in different ways using the network or not using the network, and you can see whether actually there is a gain as we are positing or not. And so this is sort of the first use case, and I guess the bottom line is that there's a lot of excitement, but it's easy to experiment with randomization strategy, which is something that's very hard to do, for instance, in a classical social studies or in a medical study. The second case study is an experiment in Honduras. This is led by Nicolas Christakis at Yale, and there's several different people involved, several different expertises. James Fowler is a political scientist, Dan Spielman is a applied mathematician, and so on and so forth. So what's interesting about this experiment is that there's 176 villages, and we're going to assign villages to different, I'll call treatment arms. So some villages will get all of the households treated, some villages will get none of the households treated, and then, that's why sort of one layer of complexity, one factor I want to test in this experiment. The other one, which I find brave and exciting, is that there are two nomination schemes that we're testing. One in which the network is mapped and used beforehand to design an experiment as well as we can. And the other scheme is not really leveraging the network mapped pre-intervention to design the experiment. And the goal of introducing this factor is to actually see to what extent having a network map pre-intervention is useful or not useful. Because you can imagine mapping a network pre-intervention is very expensive. And so in this case, my colleagues were able to raise funds to actually do that. But their interest is do I always, if I'm interested in doing the best science that I can, should I always raise money and map a network beforehand, or maybe can I get away without it, right? And so that's actually what we're trying to test here. And interestingly, the intervention is something that's been already tested, and in the literature it's known to work, and so it's really a methodological sort of goal that this experiment has. From my perspective, what's exciting is that within each village, we enlisted 26 different ways of people relating to one another. Okay, so this is just a binary representation using a combination of 3 features, but there's like 26 social metrics that we're using. Okay, and so how do we best leverage this social information, map pre-intervention to design the experiment? That's a second use case, I would say. Now, what we are interested in are network effects. Okay, so now I'm going to start introducing some jargon. In fact, the only piece of jargon I will need. Okay, so a key feature in this problem is a feature I would call interference. So the fact that the response measured on me, okay, is a function of a treatment given to other people, or say it another way, treatment given to me has effect on the response of another person. Okay, so this is something that's assumed to be zero, this effect, by classical causal inference assumptions. And so now we're going to introduce this complication, and that will have a ripple effect on what happens and what not. So just sort of have a comment saying, why do statisticians ignore typically these notions of network effect or interference and so on and so forth? Well, the reason is that interference is a known phenomenon, but you are either in the FDA use case where giving you the pill for a headache is plausibly has no effect on somebody else's level of headache, so that's reasonable, right? Or in agricultural studies, there's actually interference that's known. For instance, if I have 2 plots of land, they're neighboring, I'm testing fertilizers. If I put fertilizer in plot A, that may leak into plot B. But for that particular application, I can put guards that prevent fertilizer from leaking from plot to plot, and so I can reduce the effect of interference to be negligible, okay? So interference in those problems is a nuisance, I can limit it by design. Whereas what we're interested in a lot of the social sciences, advertising, and so on and so forth, is the causal effect of interference itself. So I cannot really assume it away. I don't want to assume it away. It's a feature, it's not a bug in my experiment, right? Okay. So now we did some work, and this is the literature scattered across social sciences, political sciences, computer science, statistics, industry, to sort of categorize what people have done. And I can point you to a reference where we categorized these problems into technical problems of interference, contagion, and homophily, depending on several things. I don't want to spend too much here, but I do want to say that there's a lot of literature. People use the same words to mean different things, and so you have to have, you have to essentially put whatever people are doing into mathematical formalism to understand exactly how these things relate. And we've done some work into that. And then, now I'm about ready to start with the technical talk. I want to have one last caveat and say there's many dimensions of complexity to this problem, which is why it swallowed me whole. Okay, so you can do testing or estimation, finite versus infinite population, randomized experiments, observational study, natural experiments, model-based, design-based, model-assisted. The network may be available to you, may not be available to you, may be available to you as a function of the intervention that you do. And so we need to decide for the rest of the talk sort of where we're going to sit, okay? And then we're going to do like average treatment effect in a finite population, sort of inferential perspective, in the context of randomized experiment. And again, maybe I would say the most interesting case in some sense is observational studies, because everyone can run an observational study and it requires more effort and money to run a randomized experiment. So our perspective was, we don't even know how to do the ideal randomized experiment. The observational study typically is an approximation of the ideal randomized experiment, so we just want to start there, okay? And so happened that, we ended up running some randomized experiments as well. Okay, so now I'm going to introduce one idea. So, okay, the way people do causal inference, there's this fundamental quantity here. People call it the table of signs. What is, well, let's think about 4 units, 2 males, 2 females.
have a binary treatment. So this Z is a vector and lives in a space of vectors. And if I have a binary treatment, then for units, this is all the possible vectors I can come up with. And there are possible ways of assigning treatment, okay? And so you can imagine that for each of these units and for each of these vectors, so 4 units, 16 columns, I can record an outcome, okay? And think of that as the fixed quantity, let's say the revenue generated by advertiser 1, or how much money spent by user 1, under one of 16 possible versions of the world. So the oracle, if you now start thinking about analysis and mathematical analysis, the oracle has access to all these quantities. They're constants, there's no randomness. Okay? If you're the oracle, you have a causal quantity you're interested in, well, you have all these quantities, just compute it. So now the problem is that as an experimenter, you're going to have to commit to run one of these possible randomizations, right? And so the randomness comes from you deciding how likely or how probable each of these vectors are, and the typical assumption is they're all equally likely. You're going to flip the coin and pick one of them, okay, at random. Let's say you pick this one in the middle where unit 1 doesn't get treated and unit 2, 3, and 4 get treated. Well, then you are going to observe 4 outcomes out of 4 times 16, and you're going to have to use those outcomes to make inference on the quantity that's defined of all the 16, okay, constants. So this notation allows you to think about all the quantities pre-intervention, an intervention that introduces randomness, and then an inferential problem of estimating something, okay, based on the outcomes post-intervention. Okay. And so the typical assumption that people do is, well, if I only observe 4 numbers and I have 4 by 16 numbers, well, that's like an unfair, difficult situation to deal with. So let's make some smoothness assumption. And the simplest assumption they will do is like, okay, yi, the outcome of unit I, is only a function of the treatment assigned to unit I. So yi is a function of zi. Well, that's great if you make that assumption and you start looking through every row. Well, for unit 1, if only z1 is relevant, okay, as an input, I only have 2 situations. I have the outcome of unit 1 under the first 8 column of the outcome of unit 1 under the second 8 column. And that's true for all the rows. And so the table becomes n times 2. So now I have 4 times 2 constants in this table of science, and I have 4 observations. And that's essentially a missing data problem, an imputation problem, and that's what causal inference means and what is done for most statisticians. Now, the moment we introduce interference in a network, there's a new notion that comes in that is interesting, is this notion of exposure. Okay? So now, not only it is relevant for my outcome whether I am treated or not, it's also relevant whether, let's say, my friends are treated or not, or whether I am exposed. And so here is a simple example. Unit I is exposed if at least one of his friends, of his neighbors, is being treated. And by using this simple notion of exposure, it's a binary notion of exposure, now instead of having 2 situations that are relevant, my outcome when treated, my outcome when untreated, I also have my outcome when exposed or when not exposed. Okay? And so here I'm just showing you a visual illustration. Unit I is in the middle, 0 means is untreated, none of its friends are treated, so this is the classical control situation. This is the classical treatment situation in blue, where unit I is treated, none of the friends are treated. This is now the new exposed situation, where unit I is untreated, but has at least one friend that's treated, and this is treated and exposed. And so these are 4 situations for the same unit, but now you can imagine if I have a network with n units, I could just look at each one of the nodes and decide whether or not each one of the nodes is one of these 4 situations. Okay, yes, David?
A good question. Does it matter when we think about this problem whether, if there's spillover effects, whether it's literally the treatment that spills over, like the fertilizer example, where the fertilizer might wash over, versus the outcome that you care about, the DV spills over. So like the plants grow high, which may actually suppress the growth of the plants in the next plot because they get less sun or whatever you process.
Yeah, that's a very
and one is treatment for I affects treatment of J. The other would be treatment of I affects Y of I, and Y of I affects Y of J. Does that matter when we're thinking about network interference?
It does. It does a lot. And so, I sort of skimmed over that slide, but, this is exactly what you're talking about, right? So in this case, you have the outcome that's relevant to the other people's outcome. And, mathematically, they're all actually different situations. So what we did, we have solutions for all the situations in isolation. And then we put them together and we say, okay, now that we know how to deal with situation ABC, what do we do if there's all, right? And I'll have a slide and an example about that, but starting simple. That's good. Thanks for pushing there. Okay, so now I was doing this conceptual experiment. Think about the network, and each unit is going to be, according to this notion of exposure, in controlled treatment, exposed, or treatment and exposed. Okay, and so that's exactly what I'm doing here. So I'm taking a graph, known pre before the intervention. I have a bunch of units, and I'm gonna sample completely at random, okay, a treatment vector where I have NT units in treatment and NC units in control, okay? And imagine doing it once for now, and that's what you get. So now if you do that, you can color code each of the units, right, as a function of how treatment was assigned, whether they are in control, they are exposed, right, or they are treated then exposed, okay? Now think about doing that one more time, a different sample, okay? Maybe you should do an animation, this reminds me. So you have a different way of assigning treatment. Now the units that were treated before or exposed before are gonna change, right? So if you imagine doing this over and over and over, you come to the realization that this way of assigning treatment is only controlling for two things: how many units are treated and how many units are exposed, right? But how many units are non-treated. But it's not controlling how many units are exposed and how many units are treated and exposed. And that is sort of like the main mode of failure of existing randomization strategies when you have a network intervention and when you have this notion of exposure and spillover and contagion. They don't control for quantities that are really relevant, like exposure and treatment and exposure. And so what we need, and where we're going, we need randomizations that control for exposures as a function of the graph, okay? So that's where we're going. And people, when you start thinking about that, say, okay, but does it really matter? Okay, so it turns out that, we can, case by case, write down situations and actually compute what would happen, okay, in a particular model of exposure, in a particular way of assigning randomization and so on and so forth, if you were to ignore, okay, the fact that there is diffusion or contagion, or there is interference and so on and so forth. And so this is just a calculation to give you an idea. Like before, I have interference from first order neighbors and additivity of exposures effect, so the model I wrote down before. And let's assume completely randomized design with n unit treated and n seat unit in control, completely ignoring the graph that exists. And we're going to estimate the average treatment effect with the difference in means estimator. We can compute the bias and the variance due to this randomization distribution, okay, if we were to ignore that. And, this is a systematic bias term. And, if you squint at it and you think what it means, well, gamma is actually how much interference matters. It turns out that if interference doesn't matter very much, exists but is not very relevant, and gamma is 0, then you have no bias. But that's great. That's one corner case. The other corner case, if you think what this is like m over n choose 2, where I have m edges and n choose 2 is the possible number of edges. So this is like the density. And so this means that if the network is sparse, interference also won't matter because you won't have too many units that are exposed, right? And you don't control for them. But in a lot of realistic setting where you do have some interference and the network are not sparse, mathematically sparse, right? Then interference matters. And we have a paper where we did a lot of these calculations for average treatment effect, total treatment effect, for the spillover effect, using different randomizations people are using. And the picture that emerged for all this calculation is that it is a problem, and people, especially in advertising or social science and political science, should sort of account for interference somehow. Okay, at the science stage, as I'm arguing here, or at analysis stage. Okay, after doing the randomization. All right, so now I'm going to give you this this idea. I'm just going to go in a very simple case through calculation, and then I'm going to revisit the classical problem of disentangling homophily from contagion. And I'm going to give you, just a formula and an insight, and then I'll talk about that problem actually at the Complex Networks conference here in Northeastern in March. Okay, so I just have a slide about that. Okay, so now, okay, let's revisit for just 1 second these two approaches to optimal design, which we call model-based and design-based. I want to have these slides because, okay, I haven't been entirely honest with you, okay? So there are situations in which the model-based approach, for instance, is actually a good approach. So what would that be? Well, think about yourself in an industrial engineering situation. Think about your 3D printing an object, okay? And you're interested in minimizing deformation of the object you're printing. Okay, that's a very well-defined problem. So what is the model there? Well, the model is physics. Physics is pretty reliable. Okay, so if your model is based on physics, or if the model can be believed, then model-based is fine. Okay, and you can totally rely on physics to design your estimator and minimize interference. And what would happen in that case? You're going to find the one optimal way of allocating treatment in my language, or the one optimal way to set the knobs of your 3D printing machine and run the experiment that way. That would be optimal. Okay. Now, if you're dealing with people or advertisers or users, there's a lot more noise in the system, and that's when you actually need to randomize. And so the notion of optimality there is not to find the optimal assignment, but is to find the optimal distribution over these columns, okay? And then once you have this optimal way of thinking about how to assign treatment, you're gonna sample from that distribution, okay? And that's what we're gonna be doing. So I'm gonna say that because, for instance, at Sloan, there's a guy called Bert Simas who is saying, oh, optimization trumps randomization in experimental design. Well, that's true if you can rely on the model, and in some application you can, so you should be aware of that. All right, so let's start from a simple toy example, okay? So this is a very practical approach, and so typically what happens is that you're gonna work with a partner, maybe an advertiser, maybe a social scientist. They know exactly what they wanna estimate. That's a spillover effect, or total lift on revenue, or so on and so forth. So somebody's gonna give you the inferential target, and they're even gonna tell you how they're gonna estimate it. They're gonna use a Horvitz-Thompson estimator, a linear weighted estimator, a difference in means estimator. That's not under your control, okay? So what's under your control is you and your collaborator are going to posit a simple, non-trivial model of the world. Okay, that's what we're going to debate about, and we're going to agree on it. And then I have this special way of using the model. So I'm going to use it to compute the mean square error of the estimator, which has been given to me before deciding the model. So it's a model-free estimator as a function of the treatment assignment. Okay, and I'm going to argue. I'm going to show you that this conditional mean square error conditional on the assignment vector is going to quantify how desirable an allocation vector Z is, and we can leverage that at design stage, okay? So first I'm going to show you this calculation, with real Y's and Z's, okay? So let's think about an homophily situation. Here the outcome of person Y is how much money advertiser I would spend in an auction is a function of whether or not he's in the standard auction or in an auction with a higher reserve price, so it's binary treatment. We observe the network G because based on past information at Google, you know which advertisers compete in the same type of auction, so for the same keyword, let's say, in search ads. And this is the model that we came up with, okay? So every advertiser has a budget Xi, and you can think of the budget in normal distribution, coming from normal distribution, mean mu and variance sigma square. And now, for in the standard auction, Zi equals 0, so the outcome, the total money spent is going to be a normal distribution with certain variance gamma square, but the mean is now the sum of the budget of the advertiser I and the neighboring advertisers. Okay,
Sorry,
that means
what's
that
X?
is the budget.
Okay.
How much money can they spend? So essentially you're saying if you're competing, in this competition network with firms or advertisers who have large budget, on average, even under no intervention, your expenditure is going to be higher. If I now put you in the treatment condition and I raise the reserve price, everyone is going to spend beta more money. So it's a very, very simple situation. We're going to assign treatment completely at random, with NT treated and C control, and we're going to use the naive estimator to estimate the average treatment effect. So this is the simplest possible situation, but here's what happens. We're going to compute this MSE for the difference in means estimator with respect to this distribution, okay? And this is what happens. And now we can look at this term. It's actually interesting. So this first term is the bias square. Mu is, the amount of the average budget square. It doesn't matter. It's a parameter that you will know.
Okay, and this is what's interesting, okay? So this is the size of the neighborhood, the average number of competitors for, the number of competitors for advertiser I. And so this sum over NT is the average number of competitors for the treated advertisers. And this is the average number of competitors for the untreated advertisers. And so to the extent there's an imbalance between treated and untreated in how many competitors they have, there's going to be a bias, okay? Okay, great. So that also suggests that if I'm designing an experiment and I know who competes with whom, all I need to do to not incur into any bias is to balance the number of competitors, okay, on average between treated and untreated. And I can do the same for variance terms, and these terms are typically the average number of competitors shared by unit I in treatment, unit J in treatment, the average number of competitors shared by unit in control, and the average number of competitors shared by unit in treatment and unit in control, okay? So, well, that's great. The practical implication is now, as I mentioned, I sort of know, or I read out of that, what desirable allocation vectors are. And these are three classes of, allocation vectors, three sets. Okay, we're going to call an allocation vector balanced if it's in this first set, and the first set only requires for the number of treated advertisers to be the same as the number of control advertisers. We're going to call it unbiased if the average number of competitors for the treated is the same as the average number of competitors for the untreated. And then, you can leverage the variance terms and come up with notions of optimality and so on and so forth. And now, basically that's the end. It's that simple, okay? Now, but it is a little deeper, and so I'm gonna try to convince you about that. But so first I'm gonna run a simulation. In the simulation I have 4 different topologies. These are artificial topologies. I'm measuring the conditional MSE on the x-axis, and I'm essentially simulating this table of science, simulating me running an experiment in different ways and comparing how well you do. Okay, so here lower is better. So this is if you run an experiment using Bernoulli, randomization or completely randomized designs, not much difference. This is if you start requiring for the allocation vector to be unbiased in the sense we just defined mathematically. This is if you decide for the allocation vector to be further restricted to be optimal in some sense by also controlling the shared number of competitors between units in treatment and control and so on and so forth. And now you can say, okay, so, but I do have a model, right? So I could use the model in 2 ways. I could use the model to decide what's desirable or not desirable, and then pick one allocation vector from that set, or I could just sample completely at random, and I could post hoc decide what's desirable, what's undesirable, right? Would that make a difference? And yes, it does, and I'll tell you why. So if you were to do this if you use the model post hoc, you do worse than if you, let's say, control the variance terms, okay? And that's actually, a non-trivial insight. Why should it matter if I, define the set beforehand and I sample from it, or since I have the same metric, I sample at random and then I decide what's good and what's bad. And the reason is the space of possible allocation vectors is vast, right? It's 2 to the n, okay? And so it does make a difference whether you know where to sample and you actually target where to sample from, or you sample at random and then you decide whether it's good or not. And it makes a difference in practice because a typical social science experiment would be, somebody's going to give me 100,000 randomizations, and then I am going to go through them with a computer program, right, to decide whether they're good or not. Maybe using a model, but that's the wrong approach, it turns out. You should not give me 100 completely random randomization. You should ask me what kind of randomization I want, and then I tell you, I want them unbiased, and you give me 100,000 of those, and now you're in a much better space, and your experiment is going to be a lot better, okay? So that's a non-trivial implication. And then, you can always trade a little bit of bias for a little bit of variance, so you can do, unconstrained optimal, and you do better, and so on and so forth. So that's basically, the practical takeaway. Now, there's a difference if you're a social scientist or if you're Google. What's the difference? Well, if we can compute the marginal MSE. That's, the marginal MSE will tell you what's the price you pay in variance if you deal with a particular given network. Now, if you're a social scientist or in our Honduras experiment, the networks are what they are, and this formula is just going to tell me, how much efficiency I'm going to lose because now it's a more complicated situation. But if you're Google, then you can actually select which 1% of the users or the advertiser you're going to target in your experiment. You can actually minimize, okay? You can select a set of 1% user or advertiser that minimizes this penalty you're going to pay. And so you're going to, there's another way to optimize, okay? And I guess, from my perspective, where I started from is, well, what does this buy me, okay? Well, this is what it buys you. What, something people call design unbiasedness. It means even if the network is, even if the model is completely wrong, you're still going to get a good number back, okay? The only price you're going to pay a price in terms of variance, and that's why model elicitation is key. That's why it's important to have a good model, but you're not going to pay a price in terms of variance. And there's the reason for it, and the reason is symmetries in this space, which I'm not going to talk about, but I do want to put the slide on, and maybe people can follow up later. It's an interesting reason why we get design unbiasedness, okay? So what I want to do instead, I want to go back to one of the problems that sort of, pushed me into this rabbit hole. And at the time when I was starting to think about design of experiments, there was 2 papers. The Obesity is Contagion paper by Christakis and Fowler, and a follow-up PNAS paper by Snanaral and colleagues on distinguishing homophily-based contagion from diffusion. Okay, so there the situation is you both have interference and they're confounding due to homophily, how to best separate the two. Okay, and the original study was an observational study, and here the question is, can we bring now this model-assisted tool to understand how we would run the optimal experiment to disentangle that, and then we can look whether the way treatment was assigned there is actually close or not close to the optimal experiment, and so on and so forth. And so what we need to do, and I won't get into the details here, but what we need to do is to essentially state a more complicated model than it was before. And this model is now going to have both treatment interference and homophily. There's also a more complicated situation. You can add contagion to that, but and you turn the crank, you compute your conditional MSE, and now the formulas get more complicated, but surprisingly still very interpretable in terms of network quantities. So this is still the bias square, and the bias square is the bias is still due to some balance or lack of balance. And then there's a variance term that also due to shared neighbors between people in treatment and control with different levels of homophily and so on and so forth. And so again, I'll talk about this at CompleteNet, but the first order result that comes out of it is now we can use that formula to come up with optimal treatment allocation to disentangle homophily and contagion in a randomized experiment. And this is sort of the picture. Think about this central unit here is an individual from a set M00, essentially in control, all the friends are in control. And this is an example, again, the central individual of a person who is exposed. So the person itself is in control, but has some of the friends that are treated. Okay. And then, how to optimally assign treatment is, well, you should only have, you should assign treatment in such a way that individuals from M00 do not share neighbors, individuals from N01 do not share neighbors, but individual, one in M00 and one in M01 do share neighbors, okay? And that's, I could talk for a while about that, but I think what's interesting is that using, for the purpose of this talk, using this model-assisted strategy in a non-trivial, interesting situation still allows you to get a notion of optimal treatment allocation, okay? And so what I want to do in a couple of minutes here is talk about the pros and cons of model-assisted approach, and have a maybe amusing anecdote about why people in industry find this interesting and useful and ended up adopting it. Okay? So, what are the advantages here? Well, it's simple and intuitive. So the conditional MSE is simple to compute or to approximate. Okay, any master student, any intern can actually do this calculation. That's good. The implied notions of balance are also easy to implement. It's essentially, it gives you more notions of balance. Now you have to balance on average degree. Well, you have a network, you can compute the average degree, treated and untreated, right? And so on and so forth. That's great. It's versatile. So, I give you a very simple situation, but you can imagine nonlinear exposure models, right? for instance, a model where having a few friends treated doesn't really matter very much, and then there's a position where the more friends you treat, well, it's going to matter a lot, and then there's a saturation period where having friends treated beyond a certain threshold, it doesn't really buy you anything. Okay. You could also have exposure as a function of unit features. For instance, in a social setting, in a social science setting, you may say, well, what does exposure mean? Exposure means that the most senior member of my tribe is being treated. If the most junior member of my tribe is being treated, it doesn't affect me, but if the most senior member is treated, right? So, you can just define different notion of exposure, and it's easy to include them in this calculation. And what we're working on right now is how to use a strategic behavior using game theory models, and how to incorporate strategic behavior into this type of design. And then, at the end of the day, having theoretical guarantees that hold even if the model completely fails, although they're only bias guarantees, not variance guarantees, is sort of interesting, okay? So there's some limitation, of course. Can all the constraints be satisfied? So in practice, in the applications I worked on, yes, but in general, not. Corner cases do exist. Think about a completely connected network. The moment you treat somebody, everyone is exposed, so that's a problem. Okay, so depending on, if you hit one of these corner cases, there may be issues. And then there's a more, maybe technical thing that I'm interested in. So it does not, so the methodology described does not offer parametric control on the space of restricted randomization, meaning I can define using balance constraints the space of restricted randomizations, but I cannot describe it analytically. I would love to, because I want to take an integral over this restricted set. Okay, but the way currently I do it is by sampling from the set. So you can only have empirical, expectations and variances, and so that's a limitation, and we're working on ways to get around that. Okay, actually using graphons to define randomization distribution, but different topic. Okay, so why is it compelling to executives? Okay, so I'm gonna have this last final slide. This is an anecdote that illustrates the turning point during my sabbatical, where we were able to convince people to commit some resources to try this. Okay, so remember that the state of the art is design based. Okay, conservative, sort of safe, very simple assignment strategies. Work really hard on the analysis. Okay, that's what my job was at the beginning. So this is a meeting with executives at Google in New York City. Think about level 7, level 8, so they have a lot of reports. These are very technical people, so it's a very fun conversation, but eventually they're gonna have to sell, what we're doing up, okay? And, up, at Google people are very technical, but, there's other constraints that come to the table, okay? And so this is just a stylized situation. So design-based approach, we run this experiment on auctions. The total lift on revenue is $1.8 million. To get an unbiased estimator, working hard on the analysis, you have this 3x correction factor, and this suggests that the amount of money the auction should have made is actually $5.4 million. So this is what I see, or what any technical person sees. Realized revenues on the actual experiment, correction factor for unbiased estimation. This is the projected revenues on the ideal experiment. Okay, and now I can see the wheels turning. Okay, they're thinking, what would an executive higher up see when I show them this formula? Well, they'll see real dollars, magic number, fantasy dollars. It's a problem. Okay. So we have a conversation about where the magic number coming from. Yes, okay, these assumptions, are they testable, untestable, are they reasonable? And the short story is, we hire an intern. 3 months later, we do the same experiment, get different number. Okay, of course there's a lot of variation, but this is like a stylized, right, anecdote. And so this is now realized revenues, because the actual experiment is the ideal experiment. Okay. And what they see finally is like there's real dollars, no magic numbers involved. Okay, but they did have to commit, an intern for 3 months to do some work. Okay, so I think that was fun, and but it does illustrate the advantages of working a little hard on the design, right? If you work a little hard on the design, the assumptions are all there at the forefront. We can agree, disagree, but then what the ideal experiment is and you run it, as opposed to, well, somebody else is going to run the experiment. That's easy. There's no thought involved. But then, somebody's going to have to come up with a magic number to
remove bias and reduce variance and so on and so forth.
And $2 million is a pretty big variance, though, right? Between the
But no, this is
fantasy
just
and
these are numbers, right? No,
Right,
the
yeah.
variance. Yeah, it's a, don't take this number seriously.
Right.
We're actually much bigger numbers, but which is why the magic number was a little bit more of an issue. But, you have to buy me a drink after that. Okay. So I just want to conclude by saying, thank you to a lot of people. My student Guillaume Bass is on the job market right now, so he's a catch. Keep an eye out for him. And a lot of former students and collaborators and people in industry. The one paper that describes some of what I talked about, and most of it, the idea, is this paper with Guillaume on model-assisted design of experiments, is published in Biometrica. And then there's some other papers that dive deeply into other things. For instance, this paper with Bishesh tells you about what happens if you ignore interference, and some other more expository paper. Thanks so much.
Questions? Yeah.
So I guess I have two questions. So the first, I was wondering if you can comment on, I guess it'd be like third order effects. How do you put those into not just friend effects, but friend of friend, especially in like an online environment where something like the way you write news could like affect a lot very quickly. The other, I guess, is like in a practical setting. I imagine like Google, like a model-based approach might be to just try and like black box out as much of the variance as you can, not worry about the bias because you're saying sort of estimate it away. You can say on the graph, it's like black box thing, and say like, you think you've estimated everything away, that could affect our beta, and now we're just going to randomly sample it. I know that theoretically that makes sense, but I'm curious if you run into like people that
Okay. So I think I'll answer the first question first, which is what do you do with third order effect? So I talked about this notion of exposure. I said, you can have nonlinear effect. You can have the most senior member of your tribe, giving an effect. You could actually make that exposure including third order effect. So in this methodology, as long as you specify analytically the notion of exposure that you work with, then some calculations become more complicated. Maybe you do exactly, maybe you approximate, but the conceptual idea is going to be fine. Okay. So then it all boils down to you do some expectations or not. So about you weren't very clear about the second question, I guess, or at least I didn't get it quite well. But what if I can paraphrase correctly? You're saying, do you run into people who essentially don't care about the notion of validity and just want to hack things? I mean, can you please maybe?
I guess the assumption in some schools, I guess, would be that we could build a model, a black box model that's good enough to estimate out any effects but the treatment effect.
So, I think it goes back to notions of variation. So when I teach statistics to my students, I always tell them, okay, where does the variability come from? In a model-based world, I try to put this very concretely on the slide at the beginning. And if you use a model, the variance comes from the model, right? So what happens is the black box fails, you're going to get a bad number because you have no control of what's happening, right? Or whether the correction factor is working or not. And you're very confident because you usually have lots of data. And so the one thing you can be sure is if you run a regression with lots of data, you get small confidence intervals, right? So the same applies to black boxes at some level. And so that is a situation where people who have to make real decisions and, whether or not the decision affect lives or just make them money faster, right? They're very cognizant of the issue, right? They don't want to find themselves in a situation where they don't know where the number's coming from and maybe they're confident about it, right? And so it's actually more likely to find yourself in a situation where people don't want to trust your new technology and all they want to do is something standard. And standard means completely randomized, cluster randomized. But then when you push them and you say, okay, why do you trust it? Because there's theory. Okay, under what condition is the theory working?
okay, well, then you start saying, well, I'm not quite sure. Can we talk about that? And then yes, the theory doesn't really work with your complication. Maybe it does, but that's a conversation to have. And and then what happens at the end is always this sort of situations. If you have a very simple assignment strategy, you could find yourself in a situation where you do want to study the effects of how your treatment affects my outcome, but because of the network and because of this random simple assignment strategy that ignored the network, you have no single person in your experiment that is not treated and has at least a person treated. And if you have no single person who is actually the one sort of case you care about, then all the inference that you can make is not based on some correction factor, right? So, and I think it's easy to also convince those people, right, that it's a conversation to have. So this correction factor comes from assumptions. Are they testable? Are they plausible? Yes, no, then we can move on from there. Good questions. Yeah.
Kind of have the same question as Kenny's question about the higher order relationships, where let's say it's not actually a social network, but the type of intervention that you need to do is an intervention on like a path in this network. So if it's an airline trying to their LAX to Houston to Atlanta leg of they're trying to do some intervention on that path in the network. Does the same? Do you still think of that as an intervention on the airport network, or is it on?
Yeah, no. So that's a very good question. I worked on transportation networks like 2 in London, but I never worked on this kind of question. And all I would say is that it sounds to me very interesting and very different from what I'm doing. You would have to define treatment differently, outcome differently. Maybe the same idea could apply, I don't know. But I haven't worked on that. But it's very interesting.
And then just the more broad question is like, to what extent outside of just social networks in general do you see this like being most useful?
I see. Well, that's a good question. So social network is not. So the way this is technically phrased, at the end of the day is there's a treatment, and the treatment affects the treatment to unit I, however you define the unit, could be a group, right? Right? It could be a path, okay? Affects other units, okay? So maybe a delay on this road is going to affect delays on this other road. So you can play with the notion of unit, right? And then the notion of exposure is different. What does exposure mean? How is this treatment on this unit or the outcome of this unit? Because there could have been a tornado that is the treatment on this path, but the plane didn't get delayed, and so what really matters at the end is the behavior, right? So once you define these things in different ways, then you can try and formalize them, right? But my guess is that as you expand the notion of treatment to be more than just unit, just one unit, the calculation is going to become a challenge. So I don't know, but great problem to think about.
So I hate to cut this short, but there is coffee and cookies on the 10th floor, so you can join us there for questions. Let's thank Edo again.